Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help demonstrate how to use basic principles of DC circuits to calculate potential differences between 2 points in a circuit. So what we're looking at is this circuit that I've made up here, and we're going to imagine we've got a battery here with an EMF that I'm going to call E1 here on the upper left. Actually, I'm going to take the 1 off of it because in my example, just to simplify it, we're going to assume that both of these batteries here and here have the same potential difference. So I'll just call that E for EMF here and here. I've thrown some capacitors in the loop here and here, and some resistors here, 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 and here. And again, just to make the math, make the video flow a little bit more fluidly, we're going to assume that all the resistors here have the same value here of 10 ohms, and the two EMFs are 12 volts, and the capacitors 30 microfarads. What we're going to do is try to calculate the potential difference between A and B. All right, so DC circuit fundamentals. First of all, let's talk about the capacitors. So when you're charging a capacitor, if you're in my class, you've seen these graphs, but I'm going to go ahead and sketch this. When you charge a capacitor, when you look at charge against time, you tend to get graphs that look like this. And they have some sort of max. They typically will hit some sort of maximum value. And once a capacitor's charge is at its maximum value, which would be like this region in our graph here, there's no more current. Because remember, current is rate that charge transfers, which is delta Q over delta T. And the current would be described by the slope of this graph, which is 0. So capacitors, when they're fully charged, are generally assumed to have a current in the branch that they're in of 0. All right, so keeping that in mind, I'm going to get rid of this. So as I look at this picture, here's a branch. It's got a capacitor in it. This capacitor is no doubt fully charged, probably to a polarity like maybe something like this. It's got a charge on it, which we'll calculate here, or no, we won't actually in the question, but it has some charge which could be calculated. But the important thing to realize is that there's going to be no current in this branch as long as this problem is a steady state type of problem, like assuming this thing is fully charged. This capacitor also will be charged probably to this polarity. It's going to have some sort of charge on it. These probably will not be the same. I'll go ahead and put a 1 and 2. But again, this problem is not a time-dependent problem. Think about it like this. Even while you've been watching this video, these capacitors should have charged up by now, or very likely will have. So this Q2 will probably be at its maximum value, which means that this branch won't have a current either. This branch can't have a current because it's not connected. These little circles here are representing the open ends of the circuit here. It is not connected across these, so we can't have a current across here. So really, current-wise, right, you have to have a closed loop to have a current. There's only one current in this problem, which is here. And I'll go ahead and calculate that current in a minute. For now, what I'll do is I'm just going to go ahead and put a current in here. Whoops. So we'll put a current, an arrow to represent the current, that direction, assuming positive charge carriers. Now before I move on to, I want to talk about potential differences. I always like to color code my potentials. I'm going to go ahead and color code red, the highest potential. Perhaps not the highest potential. I'm just going to pick a spot right here and call this the red potential. I have 2 batteries in here, so I have to kind of investigate where the potential is going to be the highest. But this potential is going to be good to this point right here. Now, if this capacitor is charged, we would get a potential difference across here. So this will be a different color, and I'll color code that in a minute. There's definitely, again, this current goes through this resistor, so we're going to have a potential drop across that resistor. I'm going to go ahead and, let's see here, use this color to represent our new potential. That's going to be good. Whoops. Yep, that's going to be good to this point right here. Same thing to there. All right. Now, let's go back and take a look at this thing. Here's a resistor here, but just like I mentioned earlier, there's no current across here because these are not connected. So there's actually no potential difference across this resistor. So this color right here goes right across that resistor. Boom, this is all at one potential. We are going to get a potential drop across this capacitor, so this will be a new potential. I'm going to go ahead and color code that one blue. Okay. Then we go on across the battery, so we've got another potential. Hit that with a light blue. This is all equipotential because it's conducting material. So this is all at constant potential up to this point and up to here. So I've got my picture kind of color-coded potential-wise. All right. Now, if I want the potential difference between A and B, if you look at the different paths, I always imagine like starting at A and walking to B. There's a bunch of different paths. I mean, here's one path. That's a pretty simple one there. All we'd have to know is the potential difference across here. You notice that this colors that kind of fuchsia to light blue, fuchsia to light blue. So that's one path. That's a pretty easy one. Other possible paths I could take, we could go across here, but there's two potential differences that we would have to calculate a potential difference at this point. We could take this path, but there's a potential there, and then another change there. And if I take this path, again, there's a couple changes, purple to orange, orange to black, black to blue. The simplest possible path to kind of investigate the potential difference between A and B is this path, because it has only one potential difference. And good news is that, again, this path right here is the only path that has a current. So I'm going to go ahead and now write a Kirchhoff's loop equation starting right here, going around clockwise. So we're going to have, for the battery, plus E for the battery, minus IR for this resistor. And remember, current always goes from higher to lower potential. Okay, minus IR for this resistor, right here. When we go across this resistor, we're going to have another minus IR. And now we're back to where we started. So the sum has to equal 0. So putting in numerical values, this is going to be 12 volts minus, and I think what I'll do here is factor out the I, and then we're going to have R plus R plus R at 10 ohms. So if you don't mind, I'll just call that 30 ohms equals 0. So our current here is going to be 12/30 amps. And when I deal with currents, I always like decimals. Oops. So 0.4 amps, and I guess I didn't really need a calculator for that. So our current here, 0.4 amps. All right, so now potential difference between A and B. What I like to do is just write a short equation here. Right? A is at a certain potential. Whatever that value is, this depends on your datum. In circuit diagrams, that depends on where your ground is. For finding potential differences, it doesn't even matter. You don't need to even define a datum. And then I just imagine walking over to B, taking into account any potential differences that I run into. So as we go across this resistor, there wouldn't be a potential difference because there's no current. Now as we go across this resistor, we are going to drop by an amount IR, because again, the current is down in this resistor. And now we're at the blue potential, right, which is constant all the way to B. So I'll just put equals potential B. This can be rearranged pretty easily. Let's call this, how about potential A minus potential B? And then we'll put this term on the right is going to equal IR, which is going to be 0.4 amps times a resistor of 10 ohms, which is 4 volts. So what we have now is that the difference in potential between A and B is 4 volts. You notice it came out positive, meaning that potential A is higher than B. Right? So it was a pretty simple math problem, but I want to talk about all the different kind of fundamentals that go into figuring out this potential difference between A and B. You have to realize where there's currents, where there's not. There's no current here because that's a presumably fully charged capacitor. There's no current in this branch because that's not connected. There is a current here. We've got a nice closed loop that goes right around like so. No current over here because we have a capacitor that again is presumably fully charged, so we'd have no current in this region. Right? Then in this example, we have a closed loop to calculate the current in our system, which I did right here. And then to calculate the potential difference between A and B, just imagine starting at A and walking over to B, allowing you to write this nice little equation out. So anyway, I hope this video helps demonstrate some principles of DC circuits. Have a great day.